We've done some analog read input in our microcontroller systems, and we've been using digital communications on USB for a while, so it's time that we found out a little bit more about this stuff. The analog read statement we've been using allows us to monitor voltages directly from sensors, analog voltages, and we could do some signal conditioning on them like amplification, but to make one measurement, we need one wire attached to one sensor, going to one input, and there's not much communication going on other than this is the signal level. It's analog all the way, and that means that it's subject to voltage drop in long cables. It's got noise, because every meter of cable picks up electrical noise, and if we want to change that, we need to find another way to talk to the sensors that won't give us these analog difficulties. Big advantages in going to digital data paths. Analog outputs are converted at the sensor or really close to the sensor, and that reduces the amount of analog noise because there's just less wire and less hardware out there in an electrically noisy environment. You can transmit multiple values on a single wire by using various data transfer protocols. So you can send not just more information, but you can share a single wire between multiple sensors. Or you can even have wireless digital data paths using radio frequency data transmission like Bluetooth, and you can include error checking and things like that so that you can get lossless data transmission. So big thing, digital data, way better than analog data if you can make it work. Two different ways to transmit data, and you should be aware of them only to know that there's a difference. Serial and parallel. Parallel transmission is more or less obsolete, and the idea was that you would use 8 lines to send data 8 times faster by sending 1 bit on each line to get an 8-bit byte over the transmission on one switch. Really important more than 30 years ago. It's still important for computer memory paths. Your 64-bit computer loads 64-bit wide words into the central processor on a memory bus that's parallel. And likewise, on our 8-bit microcontroller, we're loading 8-bit words in and out of the processor in parallel. But pretty much all external data transmission now is serial, so that it goes over a single wire per data path, and allows for multiple bits to be transmitted in a time series. So it takes a little longer than it could take in theory if we had parallel data transmission, but our serial data transmission protocols now are much faster than the old ones used to be. Speaking of old data transmission protocols, RS-232 serial communication has been around for a long time. It requires a minimum of 2 wires plus ground, and the original standard said it was going to be a 12-volt signal. It's much more common now to use the same encoding at TTL voltage levels, just 0 and plus 5 volts. So the original standard required actual plus and minus 12 volts. It wasn't particularly fast, but it was plenty fast enough for teletypewriters and things like that. Building on that, we're still using basic serial transmission, and that's actually what's going in and out of your Arduino and up to your computer. Big advantage, it's simple as long as you've somehow managed to communicate and get both ends set up the same way. If you've messed up with 9600 versus 115.200 between your settings in your sketch and the settings on the serial monitor, you've already seen this kind of problem in action. You've got to get that coordinated. It has standard speeds of 110 up to 115,200 baud, and that stands for bits per second. And you're unlikely to ever see anything under 4,800 baud. 110 baud was the speed of the early acoustic couplers that you'd attach directly to a telephone, and 1200 baud were the first personal computer modems. So 4800 baud, that would be, if it took 10 bits per character, more or less, that would be about 480 characters per second. 480 characters. That's something in the neighborhood of 60 words per second. So this is fairly fast if what you're trying to do is read some typeset data. It's not so fast if you're trying to transmit images. It's asynchronous. What that means is that both ends create their own timing clock, and they don't have any need to resynchronize with each other on those clocks, but they need to resynchronize every time they start receiving or sending a character to line up with each other. So this takes, these stop bits in the protocol, takes some added time. It can be software controlled by switching a digital output port on and off if you get the timing just right. But it's hard to do anything else at the same time because you got to get the timing just right. And there's been hardware around to do this. These UARTs, Universal Asynchronous Receiver Transmitters, provide hardware that allows you to say, send this character, and this character, and then the microcontroller can go away and do other things while the UART looks after the timing. The way you use it, you start your Arduino serial port running at 9600 baud to talk to the USB on the computer, or any other device you could attach on pins 0 and 1. And you can read back in on the serial port as well. Now, serial 1, some other microcontrollers have more than one serial port. Some even have more than 2. But you need one port for every device. So serial ports are only good for talking to one thing at a time. The baud rate, 9600 is the Arduino Sketch standard. It's slow, but it'll work on anything. 57600 is the fastest for some hardware. And 115-200 is fast enough you probably don't have to care most of the time, and it still fits in as one of the standard speeds. So this is the speed I use with almost all my sketches. RS-232 is old, but it's not obsolete. This is a state-of-the-art magnetic field tracker that we use in image-guided surgery, and the way it communicates with computer systems, any computer system, is by RS-232. And we just wrote this year, and Matt Pearson is about to defend his thesis based on some code to talk to the Aurora using Arduino to be able to track the position of some instrumentation that we want to be able to measure its location in space. Most RS-232 communications back and forth between instruments are pretty cryptic like this. They're really short. They've got things all packed in together without a lot of formatting and spacing. And the reason for that is that RS-232 isn't very fast. So if you're going to know what's going on, you need some kind of key to interpret how all of these numbers mean something when they're all packed together. The universal serial bus is much faster, and it's much more complicated to program. And it communicates with your computer to self-configure on a plug-and-play basis, which was a big deal 20 years ago, not so much now. Dedicated USB chips to handle that universal serial bus protocol drive up the cost and complexity of devices. So that might be why you would use a plain ordinary RS-232 serial rather than a USB. One of the cool things about a USB port is it provides, under the specification, up to 500 milliamps of 5-volt power. So you can run your devices off of your serial plug. That 5-volt power isn't guaranteed to be 5 volts exactly, though. It could range over plus or minus 1/4 volt. And there are some devices, including FTDI cables or similar adapters, that can talk to simple serial devices. So you can use your USB on your computer to talk to the simple serial on an Arduino with a proper cable. Now I'm going to move on to serial communication interfaces that are used typically on microcontrollers to talk to other instrumentation, usually smart instruments that are attached to them.